So the upshot of this lecture is that I give you an account on how you prove actually this big regularity theorem of Almgren, at least an idea of the main steps and what actually are all the main difficulties. Okay? So the theorem we're talking about is then essentially the following. So you have, say, a current. So T is an integer rectifiable current. Which minimizes the area locally. And now, but this minimizes the area locally, it just means the following. So if I take, say, an open set U, so let's say we are actually in the Euclidean space, although you can do it is in a Riemannian manifold, but for the sake of simplicity, let us focus on the Euclidean case, so which minimizes the area locally, and this means that if U is an open set which is inside the Euclidean space minus the support of the boundary of the current, so you have to think about it, of course, in a lot of applications you could think that the boundary of this current is just a smooth manifold, for instance, if you want to solve the Plateau problem. And otherwise, in the general situation, you can attach a notion of boundary, and then you can attach a notion of support, which is closed set. And essentially, this is kind of the closed, the smallest closed set in which, outside of which this guy vanishes. So if U is inside, then you cannot perturb T inside U and lower the area. Okay, then the theorem says that the singular set in the interior, so this is the set of points which are not in the support of the boundary, for which there is not a neighborhood in which T can be represented as a smooth submanifold times a constant multiplicity. So this set has Hausdorff dimension at most m minus 2 if m is the dimension of the integer rectifiable current. This is the theorem that one would like to prove. Okay, so one very first important point, which is a very elementary observation, but which is behind the starting points of most of the regularity theory for area minimizers, or in general for critical points of the area functionals or for stationary objects, is the so-called monotonicity formula, which is a very old thing. So the monotonicity formula tells you that when you have an area minimizing current, the amount of mass of the current, so which is usually denoted in the following way. So by this notation, we just mean if T were a smooth manifold, by this notation we would just mean the volume of the intersection of your manifold with the ball of radius r centered at x. If I divide this by r to the power m, so this quantity is actually monotone. Okay, and there are various ways of proving proving this identity. You can actually work it out from first variations, and this is maybe the most common. But a very quick and intuitive explanation of this is the following. So this inequality over here can be derived by comparing the area of your area minimizing current with an area of the cone. Okay? So a very elementary derivation of this monotonicity formula is the following. So take your ball, intersect with your ball your surface, and if you replace the surface in the ball with the cone, which has the same boundary, which has as base the intersection of the sphere with the surface, and the central point as vertex, then you get a certain inequality. And if you write down what this inequality is actually implying, is that this ratio is bigger or equal than 0. Okay? So now, M is the dimension, yes, of the surface. Okay?
This monotonicity formula relates to Bishop-Gromov comparison theorem, or it's not? It's something else.
Well, no, something else. Of course, you could. I mean, okay. So if you are, for instance, in the two-dimensional situation, being a critical point or an area minimizer means being an hyperbolic surface. So then there is a contact, a point of contact, but more in general, not necessarily. And this is the extrinsic. I mean, somehow for the surface, this is kind of an extrinsic object, right? Because I'm taking the ball in the Euclidean space. I'm not taking actually the disk in the metric of the surface, which in general I will not be able to do because my object is only defined in a weak sense. Okay? So now this basic monotonicity formula allows you to do the following procedure. So fix a point x and simply rescale your surface. So this is something that you can define the space of general currents. So you fix a point x and you fix a radius r and you magnify the surface at that point by a factor 1 over r. Okay, so you rescale the ball of radius r to the ball of radius 1. Okay, so the rescaled surface will be called pxr. So this means I fix the point x, I move it to the origin, and then I rescale by a factor 1 over r. Okay, if I am at a smooth point and I'm doing the zooming, of course in the limit I will just find the tangent plane. Okay. Now, in general, up to subsequences, these guys converge to something which is called an area minimizing cone. And the reason behind converging to a cone is because, okay, so this is, I mean, when you're kind of zooming, this function becomes closer and closer to be a constant. And somehow the kind of almost constancy of the rescaling of this function will be inherited in the limit. So in the limit, for this guy, this ratio, when I pick up x to be equal to 0 in here, will be actually constant. And this is telling you that when I'm actually replacing the surface with the cone inside, I'm not gaining any area. So intuitively, this is telling you that the final guy is a cone. Okay? Now, you could do the following. So you could attach to the cone C a so-called spline. Or actually, maybe it's spine. OK, so the spine of C is the number of invariant directions in the cone. So intuitively, the spine is the maximal vector space for which you can write your cone as a product of another cone times this vector space. Okay, so here I would need to use the language of currents. Okay, so is the, say, V of maximal dimension such that C is equal to a cone C prime times V. Okay, so this means my cone C is going to be, for instance, if V is of dimension 1, my cone C is going to be a line times a quote-unquote real cone. Okay, so for instance, the intersection of two two-dimensional planes. So the spine would be the line under which the two-dimensional planes are invariant. Okay, and then the cone C prime would be simply a cross of two lines. Okay, so the intersection of two planes, you can write it in 3D. You can write it as the intersection of two lines multiplied by another line. Okay, so this is a cone with dimension 1. And now there is a very understandable geometric principle that you can kind of imagine intuitively, and it is part of the Almgren's big regularity book. but it's a part which is like 6 pages. So this principle is telling you that, so at each point x, I can attach a number, and the number is the maximal dimension of this spine, which I see for all the tangent cones at that point. OK, unfortunately, it's a big open problem in geometric measure theory, whether the tangent cone that you get at a given point is unique. So it does not depend on the subsequence which you're taking. OK? So this uniqueness problem somehow does not allow us to speak about one tangent cone or the tangent cone. But OK, among all possible tangent cones, I can take the most homogeneous. And that gives me a number. OK? And then, so at each point x, I can attach an integer. And then after I've touched an integer, I can somehow define for every integer a stratum as j of my current T. So this is somehow the stratum of point x.
Dimension is the maximal dimension of the possible V like this?
Yes. It's the maximal dimension of the possible V like this. And then you maximize among all possible tangent cones. OK? So this is, so the stratum j is the points x such that this integer, which is the maximal of the spine of C among all C tangent to T at x, is equal to j. OK? And now you notice something somehow beautiful. What is the Sm of T? So the stratum of maximal dimension. The stratum of maximal dimension is the stratum in which there is at least one tangent cone for which this V is an m-dimensional vector space. Okay? But this C is an m-dimensional object. So if this V is an m-dimensional vector space, this C prime is simply 0. So Sm of T is the points where you have at least one tangent cone, which is a classical plane. So let us say the points x such that there exists a tangent cone at x, which is a flat plane. OK? And then there is another very simple observation which tells you that Sm minus 1 of T is empty. And the reason why Sm minus 1 of T is empty is that in Sm minus 1 of T, you would have a point x with a tangent cone, which is given by the intersection of two lines, at least, or the intersection of some lines, multiplied by a vector space of dimension m minus 1. Okay? But it's very easy to rule them out. I mean, for instance, if I have the intersection of two lines, okay, which are oriented, so say the orientation is going this way, okay, this cannot be a minimizer of the area because I can replace this current with the following current. So this is a negative point. This is a positive point. I can go here. This is a negative point. This is a positive point. I can just make these two lines, and these two lines have less area. Okay? So this is empty. OK, now the observation of Almgren, which is a very nice abstract theorem, which works in a lot of different situations, is that the dimension of each of these guys can be at most this number. Okay? So the next stratum has dimension at most m minus 2. And now it seems you are in a very good position because, of course, a posteriori you know that in the regular points have to be in the stratum M. Because in a regular point, the only tangent plane that you see is the only tangent cone that you see is the tangent plane to the regular submanifold. So you could hope that you have the reverse identity, and you could hope to say, well, at every point x where I have a tangent cone which is flat, I will actually have regularity. Okay? This is a correct statement in codimension 1. So if the ambient Euclidean space has dimension m plus 1. So And this theorem, which is essentially due to De Giorgi, although he was stating it in a different language, tells you that if the Youngian space R big N is actually R n plus 1, then Sm of t is the space of regular points, of interior regular points. And you're finished. And in fact, the regularity theory in codimension 1 allows you to exclude also further strata. So you just have to see whether there is an area minimizing cone with a certain type of singularity. And this is a celebrated work of several people which culminated in the papers by James Simons and Bombieri, De Giorgi, and Giusti, which shows that the first stratum that you encounter is the stratum m-7. And the reason is because the first singular cone that you can actually construct is a 7-dimensional cone in R8. Okay? Now, on the other hand, in higher codimension, this theorem over here is false. So you have a counterexample, and here it's one that I wrote actually the last time. So in the complex two-dimensional space, there is the following complex curve. If you look at the following complex curve at the origin, you have a singularity. But you see that if I apply this rescaling, right, when I rescale my surface by, say, R, the rescaled surface satisfies the identity R squared is equal R3 to the W3. Okay? And when I simplify the R squared with the R cubed, I see that as Z squared is equal R to W to the power 3. Okay? This is my rescaled surface. And as I let R going to 0 in this rescaling, I'm actually converging to Z squared equals 0, which is a complex line. It's a complex plane. So it's a singular point in spite of the fact that it actually belongs to the top stratum. Okay? And let me actually write down two bad examples, which will guide our analysis in the rest of the lecture. So one is the bad example, and yes?
When you consider these tangent planes, you don't consider multiplicity. So I mean.
Yeah. Okay. Yes. I was just going to touch this actually in a couple of seconds. So I will tell you in a couple of seconds. So let me just consider, just to fix ideas, that there are two examples, and one I will call the bad example, and the bad example is this guy in C2. So an honest two-dimensional surface with a singularity at the origin, and that is the very bad, actually it's very, very bad example. And we will see in a moment why. I hinted at this in my first lecture. So I just give you one possibility for this very bad example, and it's this guy. Again in C2. Now, as Jacob was pointing out correctly, so what you see over here when you're actually rescaling the surface is that over any point Z, you have actually 2 points of the surface which is sitting. Okay? So when you apply this rescaling, the 2 points are collapsing into a single point which is on the plane Z equals 0. So you're actually not converging to a simple plane, but you're converging to a plane counted with multiplicity 2. Okay? And this theory of currents is exactly made in such a way that you count multiplicities. Okay? So what, of course, could happen is that they come with opposite orientations and they cancel. And then that would be the current equal to 0. But this is not the case in here. I mean, what is really happening here is that they come with the same orientation, and so they collapse to a 2 copy of the plane. And here is actually the same. Now, this theorem is not correct, but what it is still correct in higher dimension, in higher codimension, and this is due to a first paper by Almgren in the 60s, I think, But nowadays, it's also known in a much more general situation, and usually people call this Allard's theorem because Allard is the one who proved it for more general objects, just for stationary objects. So Allard's theorem is telling you as a corollary, if the flat tangent cone that you see at the point is there with multiplicity 1, then this is still a regular point. So the obstacle to apply this regularity theory here is the presence of higher multiplicities. So in codimension 1, this theorem is true without any assumption on the multiplicity of the tangent plane that you have at the point. Okay? So if there exists a tangent plane with multiplicity 1 at the point x, then T is a C1 alpha surface in a neighborhood of x. Now, why I'm just saying C1 alpha? Well, this is what really the theorem first proves. Then, of course, once you have actually a C1 alpha surface, you have a classical surface. You can write a partial differential equation for it because you are a minimizer of the area. And then you can actually use Schauder theory, and you get C infinity or real analytic, in fact, if you are in the Euclidean space. If you are in a Riemannian manifold, you just gain as much regularity as the regularity of the Riemannian manifold allows you to get. Okay? So you get more regularity. But in the first step, you pass from your current to a C1 alpha surface. Okay? And what is the idea behind Allard's theorem, behind De Giorgi's theorem, behind pretty much all of these regularity theorems in this context? Well, the idea is the following. When you are sufficiently flat in average, okay, it's something that you still have to prove, but assuming that in average you're sufficiently flat, if you were a graph of a function, this function would have small gradients. Okay? Now, the area of a graph of a function f is the integral of, over the domain of definition, of a complicated functional, which is given by 1 plus the sum over all possible minors m of all possible sizes of the derivative of u of the determinant of m squared. Okay? Now, this is an ugly, this is a like complicated thing. Du, yes. Yes, sorry. I have the graph of f, and so this is of the f. Yes. Okay, so now when you expand this, you have the easiest minors are the 1 times 1 minors. Okay, then I don't have to take any determinant, and then the sum of all the squares of them gives you the Hilbert-Schmidt norm of the matrix. Okay, so this thing over here is 1 plus du squared. Okay, and then there are determinants of matrices which are at least 2 times 2. So if they are at least 2 times 2, the contributions that you get over here, they are at least quartic in the derivative of u. Okay? Now, if you're thinking that du is small, when you actually pick this to be small, you can Taylor expand this integrand, and you essentially find 1 plus the Dirichlet energy divided by 2, because you're expanding also the square root, plus higher order terms. And what you could hope for is that, okay, this should be actually f. And what you could hope for from this analysis is that, well, your function f at very small scales, it looks like an harmonic function. Now, the good news for this is that harmonic functions have decay properties for integrals. And what you can do with these currents is to integrate things. So what you can hope for is to pass some type of decay or some type of Morley estimate for harmonic functions to an area minimizing current under the assumption that you are sufficiently close to a plane. In particular, under the assumption that you're almost harmonic, essentially, from our analysis. And now this Morley estimate is what actually gives you the C1 alpha. And this is what can be done, and this is like the basic first idea of de Giorgi that then had been sort of generalized in several situations. Actually, Allard's theorem is not that simple. I mean, it's making a kind of different strategy, but at the core of everything you have that your function f, that your graph is almost harmonic. Okay? Now, in this example, you see that your strategy at the point 0 fails from the start. Because whichever system of coordinates you take, around the point 0, you have this branching situation. So you see in big regions, you see a function, but then below you see another function. And there's no way of describing, even up to errors, your current as the graph of a function. So de Giorgi's theorem starts by saying that if you throw away a set of small measure, actually your current under that assumption is the graph of a single function. So it's a graph of a single function plus some errors. I mean, maybe some holes or maybe some sort of weird things that might happen before you prove regularity. But here, if you want to describe your current as the graph of a single function, you have to throw away a huge portion of it, at least half of it, essentially. And then you cannot carry on this project. OK, so what was then Almgren's first idea? Well, if you think about that example over there, what you actually have is that now you cannot describe this current as the graph of a single-valued function in a neighborhood of 0, but you can describe it actually as the graph of a two-valued function. Okay? So in each point, except for the origin, you always have two values which are floating around on top of each point. Okay? If you take z as the independent variable. Okay, now, if you fix every single branch, the Taylor expansion of the area functional is still correct. So in a sense, this object, you could think about it as a two-valued graph, which is minimizing a functional, which looks almost like the sum of the Dirichlet energies of the two branches. Okay? So what Almgren did is, so we could call this kind of step 1. We could call this step 1. So regard T in a neighborhood of a branching singularity as a multi-valued function. And notice also that geometrically, you know how many values this function is taking. Okay? So if you have a q-valued function, so if the values that your multi-valued function is taking are always q, then when you make this rescaling procedure in a kind of point which looks very flat, you are converging to a plane taken with multiplicity q. So the number of values that you want to model the behavior of your current is the multiplicity of the tangent of the flat tangent cone that you're looking at a specific point x. Okay? So not only is multi-valued, but with a fixed number of values, which for historical reasons we will call q. So q will be the number of values that this is taken. Okay, and now what you want to do is you want to define a Dirichlet energy on this. Define a space W12, minimize the Dirichlet energy, and construct a theory of harmonic functions. However, your space is not a linear space. I cannot sum to two-valued functions. I don't know which branch actually have to sum to which other branch. So although this is the Dirichlet energy, this theory, and this theory is in some sense the linearization of the area functional, okay? This variational problem is not a linear variational problem. I cannot approach it in the usual way. So you don't have a description of these harmonic functions using potential theory, for instance. In general, you cannot even expect that there is actually uniqueness of minimizers, and you cannot even expect that critical points or general critical points are minimizers in this context. So it's a theory that you have to do all from scratch. Okay? So,
I have a question. So when you are saying a multi-value function, can you think about it as simply just a function to RQ, or you are looking at like in complex analysis really?
Okay, so the way to formalize it is I look at it as a map from your domain, and then I look at the product of R. I mean, in this case, for instance, it would be taking values in R2, but then taking two values, so it's taking values in R4, so in two copies of R2. But then I'm not caring about the order in which you take it. So formally, you can think about it as a map which is taking values in Q copies of Rn, and then you mod through the action of the symmetric group, which gives you, for instance, a metric space. So as long as you're not interested in Sobolev maps, if you're interested in continuous map, Lipschitz map, Hölder maps, you have a metric structure, and that is all okay. So. Yes. Okay, so yes, in that particular case, yes, but okay, so that is when you have a complex structure. But in general, this metric space. Well, okay, so you also have to decide which metric you're putting on it. Huh? So that's important. I mean, it's not only that I want a structure. I mean, I can put various structures on it, but I need a metric structure. And the metric structure that I need is going to be a structure which gives me the Taylor expansion for this, which is the correct object. Okay? So for instance, when I'm going close to a double point, okay, I cannot pick up a metric which makes the thing smooth. So in particular, if you look at this metric space in which you're taking values, it's kind of, you can identify it with a kind of very complex cone, which is made of, I don't know, certain faces which have top dimension and they are flat. But then they are attaching in a very complicated combinatorial way to some m-1 dimensional faces. And each of them are attaching in a very complicated combinatorial way to an m-2 dimensional faces and so on. So if you look at portions of this object, I mean on compact portions of this object, you actually get a polytope which has a very complicated structure. And even as a metric space for which you can attach a concept of curvature, for instance, it has a lot of bad properties. So for instance, it's not negatively curved, not even in a kind of generalized sense. It has the tendency to be rather positively curved, which makes kind of a, from the analysis from a metric space point of view, kind of ugly and complicated. Okay?
So just one. Again, can you explain again why it's not linear? Why? What is, well, yeah, here.
It's up to order, right? So I have two values, but I don't know which order. And I cannot fix an order because when I'm actually going around the branches, if I take a tour, the order actually gets flipped. So if you give me another two-valued function, I have to define arbitrarily an order for one, an order for the other, and then I can really sum up the different branches. But I don't have any insurance, for instance, that if I do this, I sum two continuous functions and I get a continuous function. I could get pretty much something discontinuous. Okay? So there's not a linear structure that you can attach to this guy. Okay, so now, what are you looking for? So you're looking for a theory which gives you well definition of this variational problem, And then you're looking at the minimizers, and the minimizers are kind of mocking minimizers of the area functional, and so you would like to have a regularity theory for these guys, right? So if you look at the George's theorem is based on the fact that harmonic functions are actually C infinity, or they're very, very smooth. So you have decay properties, which is even better, in certain sense, than being C infinity. Okay, and then you sort of make the area minimizing current. When they look like harmonic functions, or when they are approximated by harmonic functions, you make them inherit the regularity theory that harmonic functions have. Okay, so you would like to do the same here, and it's actually possible. So first of all, you can construct such a theory. Minimizing is a very well-defined property. And the minimizers are not Lipschitz. You can actually make counterexamples, but they are Hölder continuous. And you can, in fact, define regular points for a minimizer U of the Dirichlet area of the Dirichlet functional. And how do I define the regular points? The regular points are, for me, the points where my multiple valued function can be decoupled into classical harmonic functions. And since I want a geometric type of regularity, I will require that these harmonic functions, they don't cross, or they don't touch. Or as soon as the harmonic sheets actually touch, they completely collapse. So 2 copies of an harmonic function plus another harmonic function, which is sitting over here, gives me a regular 3-valued harmonic function. But if they cross, then at the points of crossing, that's a singularity. OK, so you can define the regular set of U. You can define the singular set of U as the complement of the regular set, if omega, for instance, is the domain. And Almgren's theorem tells you the dimension of the singular set is at most the dimension of the domain minus 2. So you kind of have the direct analog of what you're trying to prove in the case of area minimizing currents. OK, so all of this he did in a rather complicated fashion, and we have a paper in which we can use modern metric analysis techniques to actually recover all these results in a much cleaner way. And we have also some sort of additional results, additional problems like higher integrability of the gradient and so on. So we have additional PDE estimates. But rather than going into that, let us see what is the basic idea for getting this theorem over here. OK, so the basic thing that I want is the following. So let us look at the situation in which you are 2-valued. OK, I told you that you have a continuity theorem for this. So if you are in a situation in which you are 2-valued and you have a point where the 2 values are different, by continuity, there will be a neighborhood in which your multi-valued function, which is minimizing the Dirichlet energy, decouples into 2 separate functions. And now you can treat them separately. Each of them has to minimize the Dirichlet energy, because the Dirichlet energy of the total is the sum of the 2. So each of them has to be harmonic. So now the points are the point where actually you are, the problematic points are the points where you are collapsed. Okay? So essentially what I would like to prove is that if at a certain point you have a collapsed situation, then either you are completely collapsed into a neighborhood, or for instance, if you are 2-dimensional, that point sits isolated, and there's no guy somehow coming close to him. Okay? Then if that point sits isolated, in a punctured neighborhood, I will have the splitted situation, and I will be regular. Okay? And this would be a way of proving the theorem in the easiest situation in which you are 2-valued and in which you are 2-dimensional. Okay? So what is your enemy, therefore? So your enemy is a sequence of 2-valued points which is converging to 0. So U is collapsed at xk, but not collapsed in a neighborhood of 0. Okay? So you would like to analyze this situation. And how are you actually able to analyze this situation? So you have two basic steps. So the first step is the following. It's a very basic observation that if you take the average of the two sheets, the average of the two sheets is a classical harmonic function. I mean, outside of the singularity, you see it, because it's the sum of two harmonic functions divided by 2. So it's harmonic. Of course, that it goes harmonic through the singularities is something that you have to kind of prove without knowing regularity theory, because you don't yet have it, right? So you have to prove it from the very definition of being a minimizer. OK, once I know that the average is actually harmonic, what I could do is I could subtract it from both branches. OK, and I could have somehow now a new minimizer that has this property, that is this bed sequence. But at the bed points, since your average is equal to 0, not only you are collapsed, but the collapsed value is exactly the value 0. OK? So the first step is subtract the average. The second step is this frequency function that I spoke of in my first talk. OK, you look at this quantity, and in this context, OK, this is the Dirichlet energy. This you have to make sense of. Actually, this is like the sum. I mean, for a multi-valued function, this is just this modulus of u squared is the sum of the square of the values of each branches. So it's pretty easy. Now, the beautiful thing is that although you don't have any linearity in the space, so you can do the usual integration by parts. You don't have any potential theory, so you cannot expand by Fourier. This frequency function is still monotone. And it comes from identities which come from the first variation of the functional, which you can actually write. So this is monotone. And now it allows you to zoom into your function and take a tangent function in the limit. Not only this quantity is monotone, but when you take this tangent function in the limit, it will tell you that the tangent function in the limit has this that is identically constant, okay? Like it happens for the other monotonicity formula. And the other thing that you know for classical harmonic functions, and which is true also in this multivalued setting, is that this is constant implies that your function is homogeneous, okay? Now, imagine of rescaling along a sequence where this xk is sitting at distance 1 after you rescale it, right? So this point will be a point where the value of the function is equal to 0. So this means when I take, OK, each time I make a rescaling, then I take a limit. The limit will have value 0 in the middle, but also value 0 at some point at distance 1 from your origin, OK, by the limiting procedure. Now, if you are 0 homogeneous, I mean, if you are alpha homogeneous, you will actually have a whole half line of zeros, OK? Now, once you make a further rescaling on this line, if you were in a two-dimensional situation as we are now, after a further rescaling along points on this line, actually your function will become a function of one variable, because it will become independent on this line in which you have all zeros, okay? And now what happens is that you have, again, a situation which you can analyze by hands. So you would have a minimizers on a one-dimensional domain, and on a one-dimensional domain, you can show that you cannot have a kind of crossing. So this line would correspond to some kind of crossing, okay? And that rules out the situation that you have sort of points of multiplicity 2, which are converging to a point of multiplicity 2. So in 2 dimension, in this very special situation, I can actually show you that the singular points are isolated, okay? This is true more in general, but it's not a consequence of Almgren theorem. You actually have to do something more sophisticated, and this is something that I published with Emanuele Spadaro a few years ago. So in 2 dimension, you actually have isolated singularities. This is correct, rather than only being of dimension 0, which in terms of Hausdorff dimensions actually still allows you to be an uncountable set, for instance. OK, so far I've been talking for something like 45 minutes, but I've explained essentially 1/10 of Almgren's proof. So how do you want to go on? Well, one first thing that you want to do is you want to approximate efficiently an area minimizing current with one of these multi-valued functions in a neighborhood where your current is very flat. OK, so let me call this kind of the second step. So you want an efficient approximation theorem. So the efficient approximation theorem would tell you in a point where I'm rescaling and I see that I'm almost like a tangent plane with multiplicity q, then I throw away a set of small mass. And on the complement, I am actually a Lipschitz q-valued map, which then I can extend. And I can hope it's almost harmonic. OK? So this is a very, I mean, this is where somehow Almgren's proof starts being completely unexplored. So up to the linearized theory that I told you, there were actually several, I mean, not several, but at least a few other people in the literature still using this machinery of multi-valued functions. But when it came to this approximation theorem, it's already only the big regularity paper, which is a reference for what he is doing. OK, and we have a better approximation, I would say. So we have an approximation which picks up his estimates. But we have a better and more flexible way of doing it. So this is the content of another paper. OK? So now it comes to the two examples. So ideally, what you would like to do is the following. So once you have this approximation theorem and the first step, you could kind of adopt the following strategy. So the strategy would be assume you have a current with too many singular points where you see a flat plane of multiplicity 2 as one of the possible tangent planes. Right? I mean, OK, so somehow at step 0, if I have only, I mean, if all my points have multiplicity 1, I don't see, I mean, in all places I can apply Allard's theorem, and I'm regular. So the first instance in which I'm getting troubles are the flat points of multiplicity 2. Because the non-flat points, which are in the stratum Sm minus 2, I already know it's of codimension 2. OK, so the first thing I want to bother is these points are too many. If these points are too many, so if their dimension is more than m minus 2, I can actually find a place where I see them clustering. And this place where I see them clustering is a place where I have a flat plane, because I see a flat plane except for a set of codimension 2. Okay? And these are just too many. They're more than codimension 2. OK, so therefore, out of, say, a rescaling procedure, I hope to land in the limit to an harmonic multi-valued function, so to an harmonic two-valued function. And I would like the singular points for the current to become in the limit singular points for the harmonic function. That's what I'm hoping for. And if this were the case, since I have too many singular points for the current, I would get actually an harmonic function with too many singularities. OK? So rescaling procedure, I hope to find an harmonic two-valued map. With too many singularities. OK, but unfortunately, this strategy fails. So if this strategy would work, you would be at 1/3 of the book of Almgren, and essentially at a little bit more than 1/2 of our proof, essentially. But it fails miserably, and the reason is the following. So take this example, which I told you is the very bad example, and that is the reason why it is the very bad example. And now you see that if I try to express z as a function of w, I quote unquote see w square and then 3 branches added to them, which are the branches of w to the power 2018 divided by 3. And if I make a zooming procedure around the singularity, if I don't subtract this w to the square, I'm not seeing anything interesting in the limit. I'm just seeing a collapsed harmonic function. So, of course, this was not happening in our Dirichlet minimization, because in the Dirichlet minimization, I had the first step in which I was subtracting the average of the sheets. And by subtracting the average of the sheets, I had everything which was kind of balanced to 0. So when rescaling, if I'm seeing something, I mean, if I'm not seeing something identically equal to 0, I have to see something which is kind of has separated branches. But in here, I don't know. And you see, the tangent plane is a kind of first derivative thing. I mean, when I am actually rotating coordinates so that my tangent plane becomes flat, becomes the horizontal plane, essentially, I'm killing the first derivative in the Taylor expansion. Now here, I would have to kill the second derivative and then all derivatives until I get up to 2018 divided by 3. And you see that this 2018 is just an arbitrary number. Here, I could put whatever I want. And I would have a very, 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 very high order singular behavior, which I don't see until I actually subtract everything. OK, so here, it starts the most nightmarish part of Almgren's proof. So I would like to have a way of subtracting or a way of identifying this regular part, which in some sense, it's the average of the sheets of my current. Now, if my current were regular, I could just take the average of the sheets. I mean, if it were a regular multigraph, I would just take the average of the sheets, and that's what I actually would hope is the manifold on which I have to recalibrate everything. Okay? So this manifold on which we have to recalibrate anything anyway is called the center manifold. And this is step 3 of Almgren's proof, which is construct this center manifold. And you see something fundamental here. Even if I knew that my current were nice, before I had the linearity, I mean, before the average of the sheets was the sum of of solutions of a linear PDE. They were a sum of harmonic function. So my central sheet is harmonic. Now I have, in this particular situation where I'm very lucky, I have holomorphic branches. Then, of course, the average would be holomorphic. But in the general area minimizing situation, I have an ugly second-order partial differential equation, which is very nonlinear. And the sum of these nonlinear solutions of the nonlinear PDEs is not satisfying any PDE. So I'm not getting any estimate for this object out of the structure of my problem. So I have to kind of construct it by hand. OK, now not only I have to construct this kind of average sheet, but I also need it to construct it kind of accurately. And the reason is the following. Ideally, what I would like to do is, from this average sheet, I would like to reapproximate my current. And I would like this approximation to look almost harmonic. Now, it's an elementary computation that you can do, that if you want this approximation to look almost harmonic on this center manifold, you actually have to approximate your current using the normal bundle to this guy. Okay? So what I would like to do is to construct a surface which is at least C2, and then on the normal bundle of this, approximate my current. Now, if you remember the George's proof, or if you remember the statement of Allard's theorem, you already see that you get something extremely unlikely. So the George's theorem was telling you when the surface is very flat and it's one-sheeted, what I can show you is first C1 alpha. Then I write the PDE for it, and then I have Hauser estimates. Now, C1 alpha doesn't give me a nice normal bundle. So I need at least C2. And since in this kind of elliptic PDE things, getting C2 is usually almost hopeless, what I probably really need is some C2 alpha estimates for sufficiently small alpha. OK, things are actually even worse, because after you actually approximate on the normal bundle, if you have something which is C2 alpha and you carry on a long set of computations in which you are approximating your area functional and you're making first variation and so on, somehow at the end of, I don't know, several pages of estimates and computations, you bump into a situation in which you have to take the gradient of the mean curvature of the center sheet. And for taking the gradient of the mean curvature of the center sheet, you will need 3 derivatives for this guy. And so what actually happens is that this guy is needed to be C3 alpha. Although, OK, I don't know in Almgren's proof, but at least in our proof, out of, I don't know, 100 error terms, there is one bloody term with a derivative of h of the mean curvature. So if I could get rid of that term, actually, I would get away with a center manifold which is only C2 alpha. OK, and now this is really the part about which we are most proud, because the construction of this center manifold and of the corresponding approximation is more than half of the big regularity paper. So it's essentially, it's roughly 500 pages. And OK, this is what we accomplish actually in one single paper, which is long, but 60, 70 pages. So in here, we really do something which is making the proof much easier. And in all the other applications that I have, in which I had to construct a center manifold in a sort of fashion which is going to mimic this construction over here, you can imagine if I have to kind of stretch or modify a proof which is 500 pages, or if I have to stretch and modify a proof which is 50 pages, then this is kind of a completely different life. Okay, so up to now, I think I have constructed 5 other center manifolds, well, 4 other center manifolds in 4 other situations. If I had Almgren's proof, now I would be writing like 2,000 pages of stuff, which luckily it's not the case. OK, so let me just give you one thing which is nice. So our starting point for the construction of this center manifold was a remark of Almgren in the introduction. So an interesting thing that you see from these considerations is the following. So here you are multi-valued, but let us go back to the assumption of Allard's theorem or the George's theorem. Okay? What happens if you are just one-valued? OK, Allard's or the George is giving you C1 alpha. But this procedure, constructing the center manifold, is still working. And in fact, it has to work, because there might be some regions in which you see a collapse of the sheets. Now, this center manifold, which must be the average of the sheets, if you are one-valued, should actually be the entire current. So this means that if instead of, if you're really kind of masochistic, and instead of looking at Allard's proof, you look at the first 4/5 of Almgren's proof, you discover at the end that you have proved the same conclusion as Allard's theorem or the George's theorem, but with 2 derivatives more. So that's what he remarks over there. And so this is actually a separate paper that we had before giving the complete proof. So there is a sleek way of getting the C3 alpha regularity in the collapsed case, so of improving, if you want, in one single shot, de Giorgi's theorem from C1 alpha to C3 alpha in a reasonable way. I mean, like, using basic constructions and basic PDE methods. So there is an elementary proof of Almgren's observation. And this elementary proof is somehow the starting point for constructing this center manifold. OK, then just one last comment, and I'm finished. Of course, this is just step 3. I mean, in principle, once you have, again, made this approximation, then you have to show that this approximation is almost harmonic. And you have to show now this time that this approximation, when you zoom it, it's converging to an harmonic multivalued function, and that the singular points of the current converge to singular points of this harmonic function. And then at that point, you get the contradiction, because this would be an harmonic function with too many singular points for which the linear theory tells you it does not exist. OK, so this is not a trivial step. It's actually also kind of complicated. It's not as complicated as this step 3, but say it's at the level of the complication of step 2. So there's actually a lot of other things that I'm just swiping under the carpet somehow. After you construct this center manifold, you're by no means at the end of the story. You still have to work to actually get the conclusion. But in a sense, I would say that this center manifold is really the hardest part of the whole business. OK, that's it.
Are there any questions? So the points of multiplicity 2, they, in the end, they have to be codimension. You prove that they have to be codimension
2, yes.
And
I mean, so far I just told you the two-dimensional situation. So in the two-dimensional situation, what I will actually be able to do at the end of the day is to show that there cannot be point of multiplicity 2s which are accumulating towards point of multiplicity 2. Okay, so the point of multiplicity 2 has actually to be isolated.
okay.
This is something that you can upgrade Almgren's proof to.
So if you go back to this stratification, by, if you were to define it instead, to have a tangent plane which is, to have the spine, which, but it redefines spine as instead of being just a vector space, but a vector space of multiplicity 1.
OK, so if you just look at the tangent cones, you will not be able to kind of distinguish between these bad points of multiplicity 2 and the regular points. And somehow, by the example that I've given over here, in a sense, you will not be able to distinguish them, not even if you make a Taylor expansion to second order or to third order or to whatever. I mean, for instance, in here, to distinguish a flat point from a point where you have this behavior, you will have to go up to this order 2018 divided by 3. OK? So if you want to capture in the definition of the stratum the singular points of integer dimension, then you would have to consider everything all together. So you would have to consider the center manifold. You would have to construct for all of them a center manifold. Then from the center manifold, you would have to make a blow-up. From the blow-up, you would have to attach a tangent harmonic function multivalued. And then you're going to look at the spine of this tangent function. Because this tangent function now is going to be an homogeneous function. And so you can define a spine for it as well. Right? So this is what we kind of did in the linear theory. Of course, this is much more complicated to do. So in particular, if I want to use more refined methods like Naber and Valtorta to say that the set is rectifiable, at the moment we don't know how to do that. Because somehow to distinguish regular points from singular flat points, because this I could call a singular flat point, I actually have to look at the spine of the first non-trivial singular expansion in my wannabe Taylor polynomial of this kind. Okay.
So if you just the spine, when you define it's just, it has no multiplicity, right? You just forget the multiplicity when you say this thing.
Yes.
3 times
Yes.
okay.
Yes.
But if you were to just look at the spine with multiplicity, then you would get like multiplicity 2 or something in this very bad example. Or
Yes, you would get multiplicity 2, yes. But you wouldn't be able to distinguish it from a point of multiplicity 2 where it's actually twice a surface which is collapsed.
And that's something which you're allowed to get in your that would be a regular point?
That would be a regular point,
I
yes.
see.
And not only that would be a regular point, but that you would get. I mean, to rule out that you get actually twice a surface, you need some global geometry, because locally that is a very nice area minimizer. So for instance, after I have done the boundary regularity theory, and you tell me, for instance, that the boundary is connected, okay, then I get that the minimizer is also connected. And after I do the boundary regularity theory, I know that since at some boundary point I will be essentially 1 with multiplicity 1, I can use the connectedness to propagate this to the entire minimizer. And so at the end of the story, I would know that there is no collapse point of multiplicity 2, which is regular. So all points of multiplicity 2 must be singular. But I needed a general situation. Now, I mean, these objects could be, for instance, a minimizer in an homology class. So if you give me an homology class which per se is 2 times something, is the minimizer going to be 2 pieces, or is the minimizer going being twice the minimizer of the smaller homology class? Well, both cases can actually occur, and you can make examples. So, yeah.
So what happens if you consider this problem with non-integer currents?
If you consider this problem with non-integer currents, there's again a kind of dichotomy between the codimension 1 world and the codimension higher than 1 world. Okay, so what is the most, well, I mean, what is the simplest example of a non-integer current? I mean, for instance, I can take a family of curves in R2, and I put a probability measure on this family of curves, and then I integrate the structure of current of each curve against this probability measure. Okay, this gives me a current. Okay, in codimension 1, there is essentially the coarea formula for a BV function, which tells you that currents with a certain property in which you would minimize the mass, they all have this kind of foliation structure. And then you could try to do something. I mean, then you could actually prove theorems and so on. But in codimension higher than 1, you have situations in which you can cook up currents where that structure does not exist, this foliated structure. So for instance, there are examples in which you could take a non-integrable distribution of planes, a non-integrable distribution of 2 planes in R4, and you could attach a nice structure of currents to this, and this doesn't come from a foliation. So it's completely unclear. There's essentially no information if you leave the world of integer rectifiable currents unless you are in codimension 1. In codimension 1, you can actually still prove things.
Further questions?
But do you have an example where you get smaller area than
yes. Okay, so I quoted this example of L.C. Young. So I told you okay, so the example of L.C. Young gives you the following. So it's a so the example of L.C. Young is the following. So he has a curve gamma in R4. You take 2 times this curve gamma. Okay, and okay, so for this 2 times the curve gamma, you take the curve gamma and you take the minimizer in the integer class. And there is a competitor for this. So, I mean, you take twice this, and there is a competitor for this which has multiplicity 1 everywhere and which has less area. So this means that if I divide by 2 for this curve gamma, I have a competitor which is half of a surface, which has actually less area than the minimizer for the surface gamma with multiplicity no less than 1. And up to some time ago, there was a question whether, because you can make examples with all type of multiplicities. And there was actually a general open question whether you could by taking somehow smaller and smaller multiplicities, you could actually go to 0 even. And okay, this question has been settled negatively only very recently by Young. There is another Young because L.C. Young died somehow. But there are actual examples in which the multiplicities can actually go below. Yeah.
But not down to 0. Or yes.
Not down to 0. I mean, if I have understood it, precisely his theorems, if you try to minimize in the real homology, then you will have a lower bound for the area. Yes. And so a lower bound for the multiplicity as well.
Which depends on like topology or something like that.
Which depends on the geometry of the thing, yes. Because for every given integer, I can give you an example in which things goes bad for kind of that integer, so which means that it must depend on the fact that you have sort of fixed that particular boundary. But okay, this I actually should check. I'm not 100% sure whether he's proving something slightly different. I mean, he's proving a bound on the area from below for the whole object. Whether this gives you a pointwise bound on the multiplicity, I'm not 100% sure.